Tonight we are going to talk about one of the most misunderstood ideas in all of science. An idea that gets thrown around in movies, in science fiction, in philosophy podcasts, and in casual conversation as though it is a single coherent thing. An idea that, when you actually look at what physics says about it, turns out to be not one idea at all, but several completely different ideas that have almost nothing to do with each other, all wearing the same name, the multiverse. You have heard the word. You probably have an image that goes with it. Parallel universes, perhaps, other versions of yourself making different choices. Worlds where history went differently, where you took a different job, where a different species evolved on Earth, where the laws of physics are slightly altered. That is the popular image, and it is not entirely wrong, but it is not the whole story either, and in some ways it is not even the most important part of the story. Because when physicists talk about the multiverse, they are usually talking about something much stranger than parallel versions of familiar reality. They are talking about structures so different from anything in human experience that the word universe, the word we use to mean everything that exists, may not be adequate to describe what lies beyond it. They are talking about implications that fall out of our best physical theories, whether we want them to or not, conclusions that were not designed or wished for, but that emerge inevitably from the mathematics when you follow it honestly to its logical endpoint. And they are disagreeing vigorously about whether any of this is real physics or sophisticated metaphysics dressed up in equations. That disagreement is part of what makes this subject so interesting. The multiverse is not just a question about what exists beyond what we can see. It is a question about what it means for something to exist, about what counts as a scientific prediction, about the relationship between mathematics and physical reality. These are not simple questions. They are the deepest questions in the philosophy of science, and they are being argued about, right now, by serious physicists with serious credentials, using the most sophisticated mathematical tools available. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now make yourself comfortable. Let us begin. Let me start by doing something that is rarely done when this subject comes up in popular discussions. Let me separate the different ideas that go by the name multiverse, because they are genuinely different. They arise from different physical theories, and they have different implications and different levels of scientific credibility. The physicist Max Tegmark, one of the most systematic thinkers about this subject, proposed a classification scheme with 4 levels of multiverse. It is a useful framework, not because everyone agrees with it, but because it forces you to be precise about what you mean when you use the word. I am going to use a version of this framework tonight, though I will modify it in places where I think the physics requires it. The first type of multiverse arises from the simplest and most uncontroversial observation in cosmology. The observable universe has a finite size. Not because the universe itself is finite, but because light travels at a finite speed and the universe has a finite age. The furthest we can see is the distance light has been able to travel since the Big Bang, about 46 billion light-years in any direction. This defines the observable universe, the region we can in principle gather information about. But there is no reason to think the universe stops at the edge of what we can see. In fact, our best current cosmological models, particularly the theory of cosmic inflation, strongly suggest that the universe extends far beyond the observable horizon. not just a little beyond it, vastly beyond it, potentially infinitely beyond it. And if the universe extends infinitely, or even just very much beyond the observable portion, then by simple probability, there must be regions out there with every possible arrangement of matter, including regions that look just like our observable universe, including regions that contain exact copies of you, reading this, making the same choices, having the same thoughts. This is not a mystical claim. It is a straightforward consequence of finite probability distributions applied to infinite space. If you shuffle a deck of cards infinitely many times, every possible ordering will eventually appear. If space is infinite and matter is distributed within it according to the same quantum mechanical probabilities that operate here, then every possible arrangement of matter that is consistent with the laws of physics will be realized somewhere. Including every possible arrangement of the observable universe, including this one, the copies would not be perfect. Quantum mechanics introduces genuine randomness, but in a spatially infinite universe, there would be regions where the quantum fluctuations happened to produce something essentially identical to what we observe here. The nearest such region would be unimaginably far away. The distance to the nearest copy of you, in a universe with the density and size we observe, is estimated to be something like 10 to the power of 10 to the power of 29 meters. That is a number so large it has no analogy in human experience. The observable universe is about 10 to the power of 26 meters across. The distance to your nearest copy is incomparably larger. You would never reach it. You could never communicate with it. It is beyond any possible observation, now or ever. And yet, if the universe is spatially infinite, it exists. This is the level 1 multiverse, and it is in some ways the most philosophically unsatisfying because it offers the least drama. No portals, no wormholes, no ways of crossing between these regions. Just the ordinary universe, extended beyond what we can see, with all the mathematical consequences of infinity playing out in the dark beyond our horizon. But the level 1 multiverse is important because it establishes something crucial. The multiverse, in the sense of a reality that extends beyond what we can observe, may not be a speculative addition to our physics. It may be an inevitable consequence of the same physics that successfully describes the observable universe. If the universe is spatially infinite, and if the laws of physics are the same everywhere, and if we believe in those laws for the region we can observe, then we are already committed, by the logic of those laws, to a level 1 multiverse. The question is not whether to accept the multiverse on top of our physics. The question is whether we are willing to accept the implications of our physics when we take them seriously. Now let us move to something with more dramatic content, the level 2 multiverse, which arises from a theory called eternal inflation. To understand eternal inflation, you first need to understand regular inflation. Inflation is a theory proposed in the early 1980s, primarily by the physicist Alan Guth, to solve several puzzles about the structure of the observable universe that had no good explanation in standard Big Bang cosmology. Here is the problem inflation was designed to solve. Look at the cosmic microwave background radiation, the afterglow of the early universe that we can detect in all directions. It is extraordinarily uniform. The temperature is the same to 1 part in 100,000 across the entire sky. This uniformity is a puzzle because regions on opposite sides of the sky have never been in causal contact with each other. They are separated by distances so large that even light, traveling since the very beginning of the universe, has not had time to cross from one to the other. They have never interacted. They have never exchanged energy. How do they know to be at the same temperature? This is called the horizon problem, and it was deeply puzzling before inflation. Inflation solves it by proposing that in the very early universe, a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. Driven by the energy of a hypothetical field called the inflaton, the universe expanded by an enormous factor in an incredibly short time. A region that was initially small enough to be in causal contact, to have reached thermal equilibrium, was stretched to a size larger than the observable universe. The entire observable universe that we see today descended from a tiny, thermally equilibrated region, and that is why it is so uniform. Inflation also explains why the universe appears spatially flat, and why the distribution of galaxies shows the specific pattern of fluctuations we observe. The quantum fluctuations of the inflaton field during inflation were stretched to cosmic scales and became the seeds of all large-scale structure. Inflation has made specific, testable predictions about the pattern of temperature fluctuations in the cosmic microwave background, and those predictions have been spectacularly confirmed by observations, particularly by the WMAP and Planck satellites. So inflation is not just a speculation. It is a well-motivated theory with genuine predictive success. It is almost certainly, in broad terms, correct, though the details of the specific inflaton field and the mechanism of inflation are still being worked out. But here is where eternal inflation enters the picture. In many models of inflation, the inflaton field does not simply start inflating and then stop. It fluctuates. Quantum mechanically, it fluctuates. And in some regions, the quantum fluctuations keep the field in its inflating state, even as other regions stop inflating and settle into the kind of universe we observe. Those regions that continue inflating expand so rapidly that they dominate the volume of space, and within them, new regions continuously exit the inflationary phase and become pocket universes like ours. This process never ends. It is eternal. Once inflation starts, in many models, it keeps going forever, producing an infinite number of pocket universes, each one a big bang in its own right, each one potentially with different physical properties, depending on how the inflaton field relaxed and what other quantum fields were in their ground states when inflation ended. This is the eternal inflation picture, and if it is correct, our observable universe is just one pocket in an infinite sea of pockets. Other pockets may have different values of the physical constants, different masses for the electron, different strengths for the strong nuclear force, different cosmological constants, different numbers of large spatial dimensions. All of the parameters that we treat as fixed and given in our physics might vary from pocket to pocket, each pocket being a universe unto itself with its own laws. This is the Level 2 multiverse, and it has a feature that the Level 1 multiverse does not. The different universes in the Level 1 multiverse all have the same laws of physics, the same physical constants. They differ only in the arrangement of matter within those laws. The Level 2 multiverse contains universes with fundamentally different physics, different laws, different constants, potentially different numbers of dimensions of space and time. The implications of this are profound and disturbing in equal measure. If the physical constants can vary between universes, Then the question of why our universe has the specific constants it has, the constants that allow for the existence of atoms, stars, planets, and life, gets a new kind of answer. It is not that our constants are specially chosen or fine-tuned for our existence. It is that among all the possible pocket universes with all possible constants, only the ones where the constants fall within the range that allows for complexity, for chemistry, for biology, will contain observers to notice those constants. We find ourselves in a life-permitting universe, not because life-permitting universes are common or because they were designed, but because we can only be in a life-permitting universe. The observation selects for the observed. This argument is called the anthropic principle, and it is one of the most controversial ideas in all of physics. Some physicists think it is a deep and important insight. Others think it is a way of giving up on explanation, a way of answering the question of why the constants are what they are by saying they are what they are because we are here to notice them, which can feel like no explanation at all. The debate is not fully resolved, and it connects to questions about what it means for a physical theory to make predictions. If a theory predicts that all possible constants are realized somewhere, and we observe a specific set of constants that are consistent with our existence, has the theory predicted anything? Has it been tested? This is a genuine methodological puzzle, and it is one of the reasons the multiverse remains controversial among physicists who are otherwise committed to following the evidence wherever it leads. Now let us go to the third type of multiverse. This one does not arise from cosmology or from inflation. It arises from quantum mechanics, from the most fundamental and most successful theory of microscopic physics we have ever developed. Quantum mechanics is a theory of extraordinary precision. Its predictions match observations to more decimal places than any other theory in the history of science. It correctly describes the behavior of atoms, molecules, photons, electrons, and all the other denizens of the subatomic world. It underlies all of modern chemistry, all of semiconductor physics, all of laser technology, all of nuclear physics, and the standard model of particle physics. It is, by any measure, one of the greatest intellectual achievements in human history. And at its core, it is deeply mysterious, because quantum mechanics describes the world not in terms of definite states, but in terms of superpositions. Before you measure a quantum system, the system exists in a superposition of multiple possible states simultaneously. The electron is not spin-up or spin-down. It is both, with certain probabilities. The radioactive atom has not decayed and has decayed simultaneously until you check. The cat in Schrödinger's thought experiment is alive and dead until you open the box. When you make a measurement, when you interact with the system and record a result, one of the possible outcomes occurs. The superposition seems to collapse to a definite state. You see either spin-up or spin-down. The atom has decayed or it has not. The cat is alive or it is dead. Only one possibility is realized, but which one and why? Quantum mechanics gives you the probabilities. It tells you that spin-up will occur with a certain probability and spin-down with another, but it does not tell you which one will actually happen in any given measurement. The outcome is, according to the standard interpretation, genuinely random. There is no deeper reason why one outcome occurs rather than another. It just does with the probability the theory predicts. This is deeply unsatisfying to many physicists. It seems to leave something unexplained. Where does the randomness come from? What causes the collapse? Why does one possibility win? In 1957, a graduate student at Princeton named Hugh Everett proposed a radical alternative. Instead of the wave function collapsing when a measurement is made, Everett suggested it never collapses. The superposition simply continues. Both outcomes occur, but they occur in branches of the wave function that no longer interact with each other. From within any given branch, it appears that only one outcome occurred. But from a more fundamental perspective, both outcomes are real. Both branches of the wave function continue to evolve. Both outcomes are realized. This is the many worlds interpretation of quantum mechanics, sometimes called Everettian quantum mechanics, and it leads directly to the level 3 multiverse. Every time a quantum event occurs with multiple possible outcomes, the universe branches. Every radioactive decay or non-decay. Every photon hitting or missing a detector. Every quantum fluctuation of any kind, which means essentially everything at the subatomic level, generates a branching. Each branch is a world, and there are an inconceivable number of branches. The many worlds interpretation is not a fringe idea. It is taken seriously by a significant fraction of physicists, particularly among those who work on the foundations of quantum mechanics and on quantum computing. David Deutsch, one of the pioneers of quantum computing, is a committed Everettian. The physicist and philosopher David Wallace has written extensively and rigorously in defense of the many worlds interpretation. Sean Carroll, a prominent cosmologist and science communicator, considers it the most natural interpretation of quantum mechanics. But it is also seriously contested. The main objection concerns the nature of probability in the many worlds picture. If all outcomes occur every time, then what does it mean to say that one outcome has a higher probability than another? In ordinary quantum mechanics, higher probability means more likely to occur. But if both outcomes occur, the concept of likelihood seems to lose its meaning. How do you recover the probability rule, the Born rule, which says that the probability of an outcome is the square of the amplitude of the corresponding branch of the wave function? This is called the probability problem, or the Born rule problem, and it is the central unresolved issue in many worlds quantum mechanics. Various attempts have been made to derive the Born rule from the structure of the theory, most notably by David Deutsch and David Wallace using decision-theoretic arguments, but these derivations remain controversial. Critics argue that they assume in their premises exactly what they are trying to prove. There is also the question of what it means for a branch to split. When exactly does branching occur? How do you define what counts as a measurement or a quantum event in a way that is precise enough to make the theory work? These questions are related to the measurement problem in quantum mechanics generally, and they do not have fully satisfactory answers in any interpretation of quantum mechanics, not just in many worlds. And yet, many worlds has a feature that is hard to argue with. It is the most mathematically minimal interpretation of quantum mechanics. It takes the formalism of quantum mechanics, the Schrödinger equation, the wave function, the superposition principle, and it applies them without modification, without adding any new rules or collapse mechanisms to the entire universe. The wave function of the universe evolves according to the Schrödinger equation, always without exception, and the many worlds picture is simply what that evolution implies when you take it seriously. If you believe the Schrödinger equation, and every experiment ever performed confirms it, then you might argue that you are already committed to something like many worlds. The only alternative is to add something extra, some collapse mechanism, some modification of the Schrödinger equation, some additional rule that says when and how the superposition ends. And that additional rule has never been observed, has never been derived from anything more fundamental, and may be purely a psychological crutch to make us feel better about the strange implications of the mathematics. This is the heart of the debate about the many worlds interpretation. It is a debate about what it means to take your best theory seriously, about whether the discomfort of its implications is a reason to modify it or a reason to live with the discomfort. And it is a debate that is not fully resolved. Now let us come to the fourth type of multiverse, which is in some ways the most audacious and the most philosophically radical of all. It is the mathematical multiverse, or the mathematical universe hypothesis, associated primarily with Max Tegmark. The mathematical universe hypothesis starts from a simple observation. Our universe is extraordinarily well described by mathematics, not just approximately, not just for some phenomena, but deeply and comprehensively. The laws of physics are mathematical laws. The structure of space and time is a mathematical structure. The behavior of particles and fields follows mathematical equations with extraordinary precision. Physics as a project consists largely of finding the mathematical structures that describe the universe and deriving their consequences. Why should this be? Why should mathematics, a creation of the human mind, or perhaps a discovery about abstract logical structures that exist independently of any mind, describe the physical world so well? This is sometimes called the unreasonable effectiveness of mathematics in the natural sciences, a phrase coined by the physicist Eugene Wigner in 1960. It is not obvious why the universe should be mathematical. It is not obvious why it should not just be a collection of brute facts, of things that happen without any underlying mathematical structure. Tegmark's answer to this is radical. He proposes that mathematical existence and physical existence are the same thing, that any consistent mathematical structure exists as a physical reality, that the universe we inhabit is simply one mathematical structure among all possible mathematical structures, all of which exist with equal reality. There is no selection mechanism, no reason our structure is special. We find ourselves in this particular mathematical structure because it is one of the structures that permits the existence of observers like us. The mathematical multiverse is the largest and most all-encompassing of Tegmark's 4 levels. It includes everything. Every consistent mathematical structure is a universe. Every geometry, every set of physical laws, every possible physics, every possible reality that can be described by a consistent mathematical framework. An infinite and incomprehensibly rich landscape of being, of which our universe is one specific instance. This is philosophy, you might say. This is metaphysics. It cannot be tested. It cannot be falsified. It is not science. And that objection deserves a serious response. Because Tegmark would argue that the mathematical multiverse does make predictions, at least in principle. If all mathematical structures are real, then we should expect to find ourselves in a relatively simple one, because simple mathematical structures are more common than complex ones, in a precise mathematical sense. Our universe's physical laws are remarkably simple, as laws go. They can be written in equations that fit on a few pages. This simplicity is, in the mathematical multiverse framework, expected rather than mysterious. Whether that counts as a real prediction is debated. Whether the mathematical multiverse is science or philosophy is debated. But it is worth taking seriously as an idea, because it represents the logical endpoint of a line of thinking that starts with the observation that mathematics works unreasonably well to describe physical reality, and asks what the deepest explanation for that could be. Let me step back now and look at all four of these multiverse types together, because I want to make something clear that is often obscured in popular discussions. These four types of multiverse are very different from each other. The Level 1 multiverse, distant regions of the same space, follows directly from a spatially infinite universe with uniform laws of physics. It requires essentially nothing beyond what we already believe. The Level 2 multiverse from eternal inflation requires inflation to be correct, which there is good evidence for, and for inflation to be eternal, which follows from many specific models of inflation. The Level 3 multiverse from many worlds requires taking quantum mechanics at face value without adding any collapse mechanism, which many physicists are willing to do. The Level 4 multiverse, the mathematical universe, requires a philosophical commitment about the relationship between mathematics and physical reality that goes far beyond physics. These are different ideas with different levels of scientific support and different philosophical commitments behind them. They are not equivalent. Accepting one does not require accepting the others. And the arguments for and against each one are specific to that type, not generic arguments for or against the multiverse in general. This matters because the most common dismissals of the multiverse treat it as a single idea that is either all right or all wrong. That is not the right way to think about it. The right way is to evaluate each type on its own merits, with the specific evidence and arguments that are relevant to it. With that said, let me talk about what I think the strongest case is and what the strongest objections are. The strongest case for some form of multiverse is the combination of inflation and the fine-tuning problem. Inflation is almost certainly correct in broad outline, and eternal inflation, which follows from many models of inflation, produces a Level 2 multiverse. The fine-tuning problem, the fact that the cosmological constant and other physical parameters appear to be extraordinarily precisely tuned for the existence of complex structures, has no good explanation within a single universe. Within an eternally inflating multiverse with varying constants, it gets an anthropic explanation that, while not fully satisfying, is at least an explanation. The cosmological constant problem is particularly acute. The cosmological constant, the energy of empty space, should be enormous based on quantum field theory calculations. It should be so large that galaxies, stars, planets, and atoms could not exist. Instead, it is smaller than the theoretical expectation by roughly a factor of 10 to the power of 120. This is the largest discrepancy between theory and observation in all of physics. Within a single universe, with a single cosmological constant, there is no known mechanism that produces this cancellation. Within a multiverse with varying constants, the anthropic argument provides at least an in-principle explanation. We find a small cosmological constant because we exist in a universe where the cosmological constant is small enough to permit our existence. This is not a complete or fully satisfying solution to the cosmological constant problem, but it may be the best we have. and the fact that the best available explanation for the most extreme fine-tuning problem in physics points toward a multiverse is significant, even if it is not conclusive. The strongest objection to the multiverse, in all its forms, is the lack of testability. If the other universes exist but are forever beyond our observational reach, if we can never receive any signal from them or send any signal to them, then how do we know they are there? How do we distinguish a theory that predicts other universes from a theory that does not, if both theories predict the same observations in our universe? This is a genuine methodological challenge, and it is not resolved by simply pointing at the mathematical consistency of the theory. A theory can be mathematically consistent, it can follow logically from well-tested premises, and it can still be wrong. Mathematics is not reality. The equations do not make things real by themselves, but there are partial responses to the testability objection. Some versions of the multiverse make predictions that are, in principle, testable. Eternal inflation, for example, predicts that our universe should occasionally collide with other bubble universes during the period of inflation. These collisions would leave signatures in the cosmic microwave background, distinctive patterns of temperature fluctuations that might be detectable with future observations. No such signatures have been definitively detected yet, but the search is ongoing. The many worlds interpretation, despite its other universes being fundamentally inaccessible, is not entirely without empirical implications. The predictions of many worlds for quantum experiments are the same as the standard interpretation, but the coherent structure of quantum mechanics, the way quantum systems maintain their superpositions, provides some evidence about the structure of the theory. Quantum computing, which relies on maintaining large superpositions coherently, is implicitly testing the structure of quantum mechanics in ways that bear on the many worlds interpretation. And the mathematical universe hypothesis, while the most philosophically radical, does make the prediction that the fundamental laws of physics should be mathematically elegant and expressible in relatively simple forms, which is consistent with what we observe. None of these are the kind of clean, decisive tests we prefer in physics. They are indirect, probabilistic, and open to interpretation, but they are not nothing. The multiverse hypothesis is not entirely beyond empirical reach, even if the most dramatic parts of it, the other universes themselves, are. Let me tell you about one more thing before we close, because it connects the abstract philosophical discussion to the very concrete physics of the early universe and to observations being made right now. In 2011, the physicist Matthew Johnson and collaborators published a paper looking for signatures of bubble collisions in the Planck satellite data on the cosmic microwave background. They developed specific predictions for what a collision with another bubble universe would look like, a circular region of the sky with a specific pattern of temperature fluctuations, bounded by a sharp edge. They searched the data for such signatures and found nothing statistically significant. This is how science is supposed to work with the multiverse. You take a specific model, in this case eternal inflation with bubble nucleation, you derive specific observable predictions, and you look for them. The absence of a signal rules out some versions of the theory or constrains the parameters of the theory. It does not rule out eternal inflation entirely, but it places constraints on how frequently bubble collisions should occur. This kind of work is ongoing. The next generation of cosmic microwave background experiments, including the Simons Observatory and CMB-S4, will probe the polarization of the cosmic microwave background with far greater precision than any previous instrument. They may find evidence for primordial gravitational waves from inflation, which would constrain models of inflation significantly. They may find bubble collision signatures or tighter constraints on their absence. They may find patterns in the distribution of temperature fluctuations that favor or disfavor specific models. The multiverse is not a settled question. It is an active area of research, with specific predictions being made and tested, with specific models being constrained by data, with genuine scientific progress being made even though the most dramatic predictions, the existence of other universes themselves, remain beyond direct confirmation. That is where we are, not at the end of the story, but in the middle of it. At a moment when some of our best physical theories we have strong reason to trust based on their other predictions, seem to be pointing toward a reality that extends far beyond what we can ever directly observe. A reality that is either the greatest expansion of our picture of what exists, since Copernicus showed that the Earth was not the center of the solar system, or an elaborate theoretical construction that happens to be mathematically consistent but has nothing to do with physical reality. We do not know which. We are working to find out, and the work is some of the most interesting and most consequential science being done right now. What does physics actually say about the multiverse? It says that our best theories, taken seriously and followed to their logical conclusions, strongly suggest that there is more to reality than what we can observe. It says that the question of what that more consists of is not settled. It says that some versions of the multiverse make testable predictions and some do not. It says that the fine-tuning of physical constants, which is a real and striking feature of our universe, gets its most natural explanation within a multiverse framework. And it says that the philosophical challenges, the questions about testability and prediction, and the relationship between mathematics and reality are genuine and have not been fully resolved. It does not say that the multiverse is definitely real. It does not say that you should or should not believe in it. What it says is that the question is serious, that it arises from serious science, and that the answer, whatever it is, will teach us something fundamental about the nature of existence. That is enough to take it seriously. That is more than enough to keep thinking about it. And it is, I think, one of the most important sets of questions that anyone working at the boundary of physics and philosophy can currently be asking. The universe we can see is vast. What lies beyond it may be vaster still, or it may be nothing, or it may be everything. And we are right now in the remarkable position of having the tools, the telescopes, the detectors, the mathematical frameworks to begin to find out. Sleep well tonight knowing that the questions about what exists beyond the observable horizon are not just philosophical speculation, but active scientific research, being pursued by some of the most rigorous minds in physics, using the best tools we have ever built. The answers are coming. Slowly and completely, step by step, but they are coming. Good night. Let me take you deeper into the physics of eternal inflation, because it is one of those ideas that sounds abstract until you really sit with the mechanics of it, and then it becomes something genuinely strange and genuinely important. The inflated field, the hypothetical field that drove the early universe's exponential expansion, has a potential energy landscape. Think of it like a ball rolling down a hill. The ball starts high up, where the potential energy is large, and it rolls toward the bottom, where the potential energy is low. As it rolls, it loses potential energy and gains kinetic energy. When it reaches the bottom, the potential energy has been converted, ultimately, into the matter and radiation that we see in the universe today. In simple models of inflation, this happens smoothly. The field rolls down the hill, inflation ends when it reaches the bottom, and the universe reheats with the energy deposited by the decelerating field. Clean, simple, finite. But in more realistic models, the potential energy landscape is not a simple hill. It is more like a bumpy, complex terrain with many local minima, many valleys, many plateaus, and quantum fluctuations, which are always present and always operative, can kick the field around. They can push the field uphill, against the classical tendency to roll down. And in regions where the quantum fluctuations are strong enough to dominate over the classical rolling, the field can remain at high values indefinitely, continuing to drive inflation even as other regions have rolled down and exited the inflationary phase. This is the mechanism of eternal inflation. In the regions where quantum fluctuations dominate, inflation continues forever. These regions expand so rapidly that they always dominate the volume of the universe, even as they continuously spawn new regions where the field rolls down and inflation ends. Each region where inflation ends becomes a bubble universe, potentially with different physical properties depending on how the field relaxed and what other quantum fields did during the transition. The analogy sometimes used is a pot of boiling water. The water represents the inflating space. Bubbles of steam nucleate within it and expand. Each bubble is a pocket universe, but unlike in a pot of boiling water, where eventually all the water converts to steam, in eternal inflation, the volume of inflating space is always growing faster than the rate of bubble nucleation. There is always more inflating space. The process never ends, hence eternal inflation. This picture, if correct, means that our observable universe is one bubble among infinitely many. We can look in every direction and see up to 46 billion light-years away, but beyond that boundary, at the edge of our observable horizon, there is more space. And in that space, other bubbles have formed. Other universes exist, expanding and evolving, each with its own Big Bang, its own history, potentially its own physical constants. We cannot see them. The space between bubbles is inflating too rapidly for any signal to cross from one bubble to another after the bubbles have separated. There is a sense in which we are forever isolated, forever enclosed within our own bubble, with no way to directly observe or communicate with any other. But there is one exception. During the early inflationary period, before the bubbles have fully separated, two adjacent bubbles might collide. The walls of the bubbles might touch, and if that happens, the collision would deposit energy along the boundary, creating a disk-like disturbance that would propagate through both bubbles. In our bubble, this disturbance would eventually reach the last scattering surface, where the cosmic microwave background was formed and imprint itself as a circular anomaly. A disk of slightly different temperature, bounded by a sharp edge offset from the center of the sky. This is a specific geometric prediction, not a vague statistical tendency, but a specific shape that should appear in specific places if bubble collisions occurred. It can be searched for. It has been searched for. And so far, nothing definitive has been found. Either our bubble never collided with another, or the collision happened in a direction we have not yet fully analyzed, or the signal is too subtle for current instruments to detect, or the model needs modification. the search continues. It is science operating at the very edge of what is testable, looking for the faintest possible echoes of contact with another universe. Whether it will ever succeed, we do not know, but the attempt itself is remarkable. We are trying to detect other universes. We have a specific prediction for what they would look like, and we are building and using instruments sensitive enough to have a chance of finding that signal. That is not science fiction. That is physics in 2024. Now I want to go back to the quantum mechanical multiverse, the many worlds interpretation, and spend a little more time on what it actually implies. Because the popular picture of it, alternate versions of yourself making different choices, is true in a sense, but it is misleading in other senses, and getting it right requires a bit more precision. When Many Worlds says that every quantum event branches the universe into multiple branches, it does not mean that every mundane choice you make produces a parallel you. The branching is not at the level of your decisions. It is at the level of quantum events. Your choices at the macroscopic level are determined by the physical processes in your brain, which are ultimately quantum mechanical. So in a technical sense, your choices do lead to branchings, but the branching happens at the quantum level, not at the level of conscious experience. Moreover, the branches that result from your choices are not cleanly separated worlds in the way popular fiction depicts. The branching is a process of decoherence, of the entanglement between a quantum system and its environment becoming so complex that the different branches of the wave function can no longer interfere with each other. This decoherence happens extraordinarily quickly, in fractions of a second, for macroscopic systems. By the time you are aware of a decision, the quantum branching has already occurred, and the branches have already decohered beyond any possibility of recombination. But decoherence does not mean the branches are separate universes in any physical sense. They are all part of the same universal wave function. They just do not interact with each other anymore. They cannot send signals to each other. They cannot affect each other. They evolve independently from that point on. In practice, they are as separate as if they were different universes, but the mathematical description sees them as parts of a single structure. This matters for the question of whether the many worlds multiverse is real or metaphysical. The other branches of the wave function are not postulated in addition to the physics. They are part of the physics. The universal wave function, evolving according to the Schrödinger equation, contains all the branches. If you believe the Schrödinger equation, you believe the branches exist, in whatever sense the wave function exists. The question is what that sense is. Do the branches exist as physical realities in the same way that particles and fields exist? Or are they just mathematical possibilities, amplitudes in a probability distribution, convenient fictions that help us calculate outcomes? This is the deep question in the philosophy of quantum mechanics, and it does not have a universally agreed upon answer. What I can say with confidence is this. The many worlds interpretation takes the Schrödinger equation seriously as a description of reality, applies it without modification, and derives the appearance of probability and the appearance of wave function collapse as consequences of decoherence and the structure of the wave function. Whether you find that compelling, whether you think the mathematical branches are real or merely computational tools, is a question that touches the deepest issues in philosophy of physics, and it matters practically as well as philosophically. The interpretation of quantum mechanics that you adopt affects how you think about quantum computing, about quantum information, about the nature of entropy and irreversibility, about the arrow of time. These are not just abstract philosophical questions. They are questions with practical implications for the most advanced technologies we are currently developing. Let me also say something about the relationship between the different types of multiverse that is sometimes missed. The Level 2 multiverse from eternal inflation and the Level 3 multiverse from many worlds are not independent. Both are implied by the same physics. If inflation is correct, and if quantum mechanics is correct, and if we take both seriously without adding additional rules, then we get both the eternally inflating Level 2 multiverse and the many worlds Level 3 multiverse simultaneously. The Level 2 multiverse arises because quantum fluctuations during inflation cause different regions to exit inflation at different times and with different properties. The Level 3 multiverse arises because those quantum fluctuations themselves branch the wave function. In the many worlds picture, all the different outcomes of those quantum fluctuations occur in different branches of the universal wave function. The Level 2 multiverse is, in this view, contained within the Level 3 multiverse. All the different bubble universes with different physical constants are different branches of the wave function of the eternally inflating universe. This nesting of multiverse types within each other is one of the reasons the subject is both fascinating and confusing. The boundaries between the different types are not sharp. They depend on how you interpret quantum mechanics and how you think about the relationship between the wave function and physical reality. Different physicists making different philosophical choices about these foundational questions end up with different pictures of how the multiverse is structured. What is not in dispute is that the physics point somewhere in this direction. Our best cosmological theory and our best theory of the microscopic world, both of which are extraordinarily well tested in the domains where we have data, both seem to be pointing toward a reality that is larger and stranger than what we can directly observe. Whether that reality consists of distant regions of the same space, of separate bubble universes with different laws, of many worlds branches of a universal wave function, or of all possible mathematical structures, depends on questions that are not yet resolved. But the pointing is real. The direction is clear, and the work of following the physics wherever it leads, even when it leads to uncomfortable or vertiginous conclusions about the nature of existence, is the core of what science is. Let me close with something personal, not about me, but about what it feels like to sit with these ideas seriously. There is a particular kind of vertigo that comes from really engaging with the multiverse hypothesis. Not the comfortable, exciting vertigo of science fiction, where other universes are places you can visit and worlds you can explore, but the deeper, stranger vertigo of realizing that if these ideas are right, everything you know is a tiny, biased sample of what exists, that the universe as you know it, 8 billion years old, 93 billion light years across, containing 2 trillion galaxies, which already seems incomprehensibly large, might be one point in an infinite landscape of possibility. That your entire life, your choices, your history, your experience, might be one branch among uncountably many. That the physical constants that determine the character of reality as you know it might be just one set of values among all possible values, realized in this region, different elsewhere. That vertigo is, I think, the appropriate response. Not denial, not dismissal, not the comfortable retreat to saying that what we cannot observe does not matter. but genuine engagement with the strangeness of what our best theories are saying. Genuine openness to the possibility that reality is far larger and stranger than our evolved intuitions can naturally encompass. The history of science is a history of exactly this kind of expansion. The Earth was not the center of the solar system. The Sun was not the center of the galaxy. The Milky Way was not the only galaxy. The observable universe was not the whole universe. At every step, the domain of what we thought of as everything turned out to be a small and unrepresentative sample of what actually exists. The multiverse is the next step in that sequence. We do not know if it is real. We are working to find out, but the pattern is clear. Every time we have thought we knew the boundaries of existence, those boundaries have turned out to be the boundaries of our observation, not the boundaries of reality. Whatever the answer turns out to be, the multiverse question is asking us to take seriously the possibility that we are, once again, vastly underestimating the scale of what is. That is worth losing some sleep over. Good night. Let me go deeper into the fine-tuning problem, because it is the empirical heart of the case for the multiverse, and it deserves more time than it usually gets in popular discussions. Most presentations of fine-tuning give you a few impressive-sounding numbers and move on. But to really understand why physicists take this seriously, you need to understand what fine-tuning means technically, what kinds of constants are fine-tuned, and why the alternatives to the multiverse explanation are unsatisfying. Fine-tuning, in the technical sense, means that a parameter has a value that falls within a very narrow range of all possible values, where values outside that range would produce a universe radically different from ours, specifically a universe without the kind of complexity that allows observers to exist. The narrowness of the range is what makes it puzzling. If a parameter could take any value from 0 to some large number, and the value required for our kind of universe is a tiny fraction of that range, then getting that value by chance seems extraordinarily unlikely. Let us walk through some examples. The cosmological constant, the energy density of empty space, is the most extreme case. Quantum field theory predicts that the vacuum should have an energy density of roughly 10 to the power of 93 grams per cubic centimeter, based on the contributions of quantum fluctuations of all the fields in the Standard Model. The observed value is about 10 to the power of negative 29 grams per cubic centimeter. These differ by a factor of about 10 to the power of 122. If you were randomly selecting a value for the cosmological constant from anywhere in the theoretically natural range, the probability of landing within the range that allows for galaxy formation is something like 10 to the power of negative 122. That is a number so small that it is effectively zero. The cosmological constant is, by any measure, the most severe fine-tuning problem in all of physics. The strong nuclear force coupling constant is fine-tuned at a less extreme but still remarkable level. If the strong force were a few percent weaker, protons and neutrons would not bind together in nuclei, and atoms would not exist beyond hydrogen. If it were a few percent stronger, the diproton, two protons bound together without neutrons, would be stable, and nuclear fusion would proceed so rapidly in stars that they would burn out almost instantly. The range of strong force coupling constants that allows for a rich nuclear chemistry, and therefore for the chemistry of life, is narrow. The ratio of the electromagnetic force to gravity is enormous. about 10 to the power of 36. This ratio determines, among other things, the mass of stars and the timescale on which they burn. If gravity were much stronger relative to electromagnetism, stars would be much smaller and shorter-lived, not giving enough time for planetary systems to develop complex chemistry. If it were much weaker, stars would be much larger and more violent. The specific value of this ratio seems, at least naively, to require explanation. The mass of the electron compared to the mass of the proton is about 1 to 1836. If the electron were much heavier, the energy levels of atoms would be very different, and the chemistry of complex molecules would not work. If it were much lighter, the same. The specific ratio that allows for the rich chemistry of life seems, again, to require explanation. The list goes on. The density perturbations from inflation, the seeds of structure formation, are fine-tuned at the level of about 1 part in 100,000. If they were much larger, the universe would have collapsed into black holes. If they were much smaller, no galaxies would have formed. The specific amplitude that allows for galaxies, stars, and planets is, again, a small fraction of the theoretically possible range. Now, what are the possible responses to all this fine-tuning? The first response is to say it is all a coincidence. The constants just happen to have the values they have, and the fact that those values are life-permitting is a remarkable coincidence, but remarkable coincidences do happen. This response is unsatisfying because it offers no explanation. It says, essentially, we got lucky, and it provides no framework for understanding why. The second response is to say that the constants are fixed by some deeper physical theory that we have not yet discovered. Perhaps there is some unified theory of everything that derives the values of all the constants from first principles, showing why they could not be otherwise. String theory, for example, was hoped by some of its proponents to uniquely determine the values of the physical constants. But as string theory has developed, it has become clear that it does not uniquely determine them. Instead, it produces an enormous landscape of possible solutions, each with different effective physical constants, which is itself an argument for a multiverse rather than against it. The third response, and the one that the multiverse hypothesis offers, is that the constants are not fixed but vary between different regions of the multiverse, different bubble universes, different branches of the wave function. In this case, the question of why our universe has life-permitting constants gets an anthropic answer. Most universes do not have life-permitting constants, but universes with life-permitting constants are the ones that contain observers. So observers necessarily find themselves in universes with life-permitting constants. The observation is not surprising. It is guaranteed. This anthropic reasoning is the key philosophical move in the multiverse response to fine-tuning, and it is the most controversial part. Critics argue that it is empty, that it explains nothing, that saying we must observe life-permitting constants because we exist is circular. Defenders argue that it is a genuine explanation, that it converts what looks like a staggering coincidence into an observation selection effect, similar to the observation that we find ourselves on a planet suitable for life rather than in the vacuum of interstellar space. The debate about anthropic reasoning is not primarily about physics. It is about logic, about what counts as an explanation, about the relationship between observer selection effects and physical laws. It is, at its core, a philosophical debate, and philosophical debates are rarely resolved cleanly, but they can make progress. One way the debate can make progress is through predictions. The multiverse plus anthropic reasoning makes predictions. Not about individual constants, but about the statistical distribution of constants across observers. If most observers in the multiverse observe a cosmological constant much smaller than the theoretically natural value but not zero, the multiverse predicts that we should observe a small but non-zero cosmological constant. We do. The observed cosmological constant is small but non-zero, which is consistent with the multiverse prediction. This prediction was actually made by Steven Weinberg in 1987, before the cosmological constant was measured. Weinberg argued that if the cosmological constant could take different values in different pocket universes, then most observers would be in universes where the cosmological constant was the largest value consistent with galaxy formation. Anything larger and galaxies would not form, so there would be no observers. Anything much smaller and the probability would be low, because small values require more cancellation between the large, theoretically natural contributions. The measured value of the cosmological constant is in good agreement with Weinberg's prediction. This is a genuine predictive success for the multiverse framework, though it depends on assumptions about the distribution of cosmological constant values across the multiverse that are not fully justified. Whether you find this compelling or unconvincing probably depends on your prior views about what scientific explanation requires. If you think a theory must make sharp, unique predictions to be scientific, then the multiverse is not scientific in this sense. If you think that statistical predictions about the likely value of a parameter given an assumed distribution, are legitimate scientific predictions, then the multiverse has genuine predictive success. I am not going to tell you which view is right. Smart, careful people disagree. What I will say is that the question is not trivial, and that dismissing the multiverse as unscientific because it is untestable is too quick. The testability question is nuanced, and the multiverse does have some empirical content, even if it is not the kind of clean falsifiability that characterizes the best-case scenarios in science. Let me now spend some time on the implications of the multiverse for one of the deepest questions in science and philosophy. The question of why there is something rather than nothing. This question has haunted philosophy since antiquity. Why does the universe exist? Why is there matter, energy, space, time, physical laws? Why is there anything at all, rather than complete nothingness? Within a single universe, this question has no scientific answer. The existence of the universe is simply a brute fact. Physics describes how the universe evolves from its initial state, but it does not explain why there is an initial state, or why there are physical laws, or why there is anything for those laws to act on. The question of why there is something rather than nothing lies within single universe physics, outside the domain of science. But within the mathematical multiverse, Tegmark's level 4, the question gets a different treatment. If all consistent mathematical structures are realized as physical realities, then the question of why our mathematical structure exists becomes less pressing. Our mathematical structure exists because all mathematical structures exist. The question shifts from why does our universe exist to why are we in this particular universe rather than another, which gets an anthropic answer. We are in a universe compatible with our existence because we can only be in such a universe. And the deeper question, why do mathematical structures exist at all, may have a different character than the question of why a specific universe exists. Mathematical structures are not physical objects that might or might not exist. They are abstract logical structures whose existence is a matter of logical necessity, not physical contingency. 2 + 2 = 4 is not a fact that might have been otherwise. It is a necessary truth. If mathematical existence is like this, logically necessary rather than physically contingent, then the existence of the mathematical multiverse is not something that needs to be explained. It is just true necessarily. This is a deeply controversial philosophical position. Many philosophers reject it. The relationship between mathematical existence and physical existence is one of the oldest and hardest questions in the philosophy of mathematics, and Tegmark's resolution of it by identifying them is, to put it mildly, not universally accepted. But the attempt is interesting. The mathematical universe hypothesis is trying to answer the deepest question about existence by dissolving the distinction between abstract mathematical truth and physical reality. Whether it succeeds is a question that philosophers and physicists will be debating for a long time. What I find most interesting about the whole landscape of multiverse ideas is not any specific version of it, but what they collectively represent. They represent the physics of the early 21st century, grappling seriously with questions that were previously the exclusive domain of philosophy and religion. The question of what exists, of what the universe is and how it came to be, of why the laws of physics are what they are. These are questions that science is now engaging with more rigorously than at any previous point in history. The tools are more sophisticated. The observations are more precise. The theoretical frameworks are more powerful. And the questions are deeper, because the more we learn, the further the horizon of the unknown recedes, and the more we can see of the landscape we do not yet understand. The multiverse, in all its forms, is a child of this moment. It is what happens when the most successful theories in the history of physics are followed to their logical conclusions, without apology and without pulling back from the implications because they are strange or uncomfortable. Whether the multiverse is real, in whatever sense the word real can apply to things beyond our observational reach, we do not know. It might be the most important discovery in the history of science, the realization that our universe is one of an enormous number of universes, each equally real, each equally part of the total structure of existence. Or it might be an elaborate theoretical fantasy, beautiful mathematics that does not correspond to physical reality, a wrong turn taken by following our best theories too literally. We are working to find out. The search for bubble collision signatures in the cosmic microwave background continues. The study of quantum foundations and many worlds continues. The development of string theory and its landscape of possible universes continues. The philosophical analysis of what the multiverse hypothesis means and what it would take to confirm or disconfirm it continues. And the night sky, full of light that has been traveling for billions of years to reach your eyes, is one more thing to add to the context. Every photon that reaches your eye is a messenger from the universe we know. Beyond the horizon from which those photons came, beyond the 46 billion light-year boundary of the observable universe, the physics we have developed gives us reason to think there is more, possibly much more. Possibly everything. That is the multiverse. That is what physics actually says about it. Sleep well tonight knowing that the universe you inhabit might be one of an incomprehensible number of universes, each as real as ours, each running its own physics, each containing its own history. Or it might be the only one. We are trying to find out. And the trying, the rigorous, humble, creative, and endlessly curious trying is one of the finest things our species does. Good night. There is a specific calculation I want to walk you through, because it is one of the most striking things in the whole multiverse discussion, and it is rarely presented clearly. It is the calculation of the distance to the nearest copy of the observable universe in a spatially infinite cosmos. Start with the observable universe. It contains roughly 10 to the power of 80 atoms. Each atom can be in various quantum states. The total number of distinct quantum states that the observable universe can be in is something like 2 to the power of 10 to the power of 80. This is an incomprehensibly large number. It is a 2 followed by 10 to the 80th zeros. No number of this magnitude has any analogy in everyday experience. Now, in a spatially infinite universe with a uniform density of matter, every possible quantum state of the observable universe that is consistent with the laws of physics is realized somewhere. The question is how far away the nearest region that is in the same quantum state as our observable universe. The answer depends on assumptions about the distribution of matter and the nature of the initial conditions, but a rough estimate goes like this. You need to survey regions of the universe of the same size as the observable universe until you find one in the same state as ours. The probability of any given region being in the same state is 1 in 2 to the power of 10 to the 80th. So you expect to need to check about 2 to the power of 10 to the 80th regions. Each region has a diameter of about 10 to the power of 26 meters. So the nearest copy is about 10 to the power of 26 times 2 to the power of 10 to the 80th meters away. That number is almost beyond description. The observable universe is 10 to the power of 26 meters across. The number of Planck volumes in the observable universe is about 10 to the power of 185. The number of atoms in the observable universe is 10 to the power of 80. None of these numbers are even remotely in the same ballpark as 2 to the power of 10 to the 80th. And yet, in an infinite universe, the nearest copy of you is out there, at that distance, beyond any possibility of contact, communication, or observation forever, but there. This is what infinity means when you apply it to physics. It does not just mean very large. It means that everything that can happen does happen somewhere. The nearest version of you who made a different choice this morning exists at that distance. The nearest version of Earth where the asteroid that killed the dinosaurs missed exists at that distance. The nearest version of our galaxy where life never arose exists at that distance. All of these are separated from us by numbers that dwarf any quantity we normally encounter in physics or in daily life. The level 1 multiverse is not speculative in the way the other types are. It follows from essentially nothing more than the assumption that the universe is spatially infinite, which is consistent with current measurements. The flatness of the observable universe, confirmed by multiple lines of evidence, suggests that if the universe is finite, it is much larger than the observable portion. And if it is infinite, then the level 1 multiverse follows directly. We do not need inflation. We do not need quantum mechanics. We just need the universe to be large enough, which it almost certainly is. This should be more disturbing than it usually is. The existence of the level 1 multiverse, distant regions with every possible arrangement of matter, is almost certainly true if the universe is spatially infinite. and we have no strong reason to think the universe is finite. The assumption of spatial infinitude is the null hypothesis, the default assumption in the absence of evidence to the contrary. So when people ask whether the multiverse is real, they should first ask whether the universe is spatially infinite. If it is, the level 1 multiverse is real, almost by definition. The copies of you exist. The parallel Earths exist. They are not in other dimensions or other timelines. They are in the same space as you, separated by distances so large that the word far does not begin to capture the separation. Now I want to spend some time on a question that goes to the heart of the philosophical debate about the multiverse. It is the question of what we mean by real. When a physicist says that something is real, they usually mean that it has observable consequences, that it interacts with other things in ways that can be measured, that it leaves traces in detectors and experiments. The electron is real because we can measure its mass, its charge, its spin, its effects on atoms and molecules, and on the macroscopic world. The photon is real because we can detect it with instruments sensitive to light. Even quarks, which are confined inside protons and neutrons and can never be isolated, are real in this sense because they have measurable effects on the properties of protons and neutrons. But the other universes in the level 1 or level 2 multiverse cannot be detected. They cannot be measured. They cannot leave traces in our instruments. They are, by definition, beyond the observable horizon. Does that mean they are not real? This question reveals a deep tension in our concept of physical reality. On one hand, we want to say that what is real is what interacts with us, what we can in principle measure. On the other hand, we routinely accept the reality of things we cannot directly observe, things like the inside of a black hole, or the first femtosecond after the Big Bang, or the quantum state of a particle before measurement. We accept these as real because they are implied by our best theories, even though they are not directly observable. The other universes in the level 1 multiverse are implied by our best cosmological theories in exactly this sense. If the universe is spatially infinite and the laws of physics are uniform, then those regions exist in exactly the same sense that the inside of a black hole exists or the early universe exists. They are beyond our observational reach, but they are part of the same physical reality that our theories describe. Whether you call this real is partly a matter of philosophical preference. Some philosophers of science adopt a verificationist position, according to which something is real only if it can in principle be observed or detected. On this view, the level 1 multiverse is not real because its components are forever beyond observational reach. Others adopt a more realist position, according to which our best theories describe a mind-independent reality that may extend beyond what we can observe. On this view, the level 1 multiverse is real if our best cosmological theories are correct. I do not think there is a fact of the matter here that can be discovered by physics. The question of what counts as real, of what our theories are about, is philosophical in character. Physics can tell us what our theories predict. It cannot tell us what the predictions mean for the nature of reality. That requires philosophical interpretation, and reasonable people, taking physics seriously, can reach different conclusions. What I do think physics can tell us is this: the observable universe is almost certainly not all there is. Whatever lies beyond the observable horizon, whether it is more of the same in a level 1 multiverse, or radically different bubble universes in a level 2 multiverse, or branches of a universal wave function in a level 3 multiverse. There is something there. The assumption that the observable universe is the totality of existence is not supported by our best physics. It is, in fact, contradicted by it. And engaging seriously with what might be there, even if we cannot observe it directly, is not unscientific. It is what physics has always done. Newton posited forces acting at a distance that could not be directly observed, only inferred from their effects. Maxwell posited electromagnetic fields pervading all space, invisible and undetectable except through their effects on charges and magnets. Einstein posited spacetime curvature, invisible to direct inspection, but inferred from the motion of objects. Dark matter is posited on the basis of its gravitational effects, though it has never been directly detected. The multiverse is different from these in one important respect. The other universes, unlike dark matter or electromagnetic fields, are not predicted to have any direct effects on things we can observe in our universe. They affect our understanding of probabilities and of why our universe has the properties it has, but they do not cause anything we can directly measure. This is what makes the multiverse more philosophically challenging than dark matter or electromagnetic fields. But it is worth noting that some forms of the multiverse are closer to the observable realm than others. Bubble collisions in the level 2 multiverse would, if they occurred, and if we look in the right direction, leave signatures in the cosmic microwave background. Many worlds' branches, while they do not communicate with each other, are part of a theoretical framework whose other predictions, the quantum mechanical predictions for everything we can observe, are extraordinarily well confirmed. The multiverse is not a single thing with a single level of scientific credibility. It is a family of ideas, ranging from the almost certainly true level 1 to the philosophically radical level 4, with different levels of empirical support and different relationships to our best established theories. Taking it seriously requires taking all of this complexity seriously, not dismissing it as speculation, and not accepting it uncritically as established science, but engaging with the specific arguments, the specific evidence, the specific predictions, and making judgments based on the full picture. That is hard. It requires holding a lot of uncertainty. It requires being comfortable with not knowing, with being at the frontier of human understanding where the answers are not yet in and may not come for a long time. But that discomfort, that intellectual honesty about the limits of what we know, is the foundation of genuine understanding. The multiverse is where physics is pushing right now. It is one of the central questions at the frontier of the field, and the answer, whatever it turns out to be, will be one of the most important discoveries in the history of science. We are at the beginning of finding out. That is the most exciting place to be. Sleep well. The universe or universes will still be there when you wake up, and so will the questions. Good night. Let me talk about string theory and the landscape, because it is one of the most important developments in the relationship between theoretical physics and the multiverse idea, and it is also one of the most controversial. String theory is a theoretical framework that attempts to unify all the fundamental forces, including gravity, within a single mathematical structure. It does this by replacing the point particles of the standard model with tiny, vibrating one-dimensional strings. Different vibrational modes of the string correspond to different particles. Gravity emerges naturally from the theory as one of these modes. The theory requires additional dimensions of space beyond the 3 we observe, typically 6 extra dimensions, compactified at scales far too small to detect with current instruments. String theory has been an extraordinarily active area of research for 4 decades. It has produced deep mathematical insights, connections between seemingly unrelated areas of physics and mathematics, and a rich theoretical framework. But it has not, in 40 years, produced a single confirmed experimental prediction that distinguishes it from other theories. It has not told us what the masses of the particles are, or why the cosmological constant has the value it has, or what dark matter is. It has remained, stubbornly, at the level of mathematical structure rather than empirical prediction. Part of the reason for this is the landscape. When string theorists tried to find the specific version of string theory that corresponds to our universe, they discovered that the theory has an enormous number of solutions. Different ways of compactifying the extra dimensions give different effective physics in 4 dimensions, different particle masses, different force strengths, different cosmological constants. The number of consistent solutions is estimated to be something like 10 to the power of 500, a 1 followed by 500 zeros. This is what is called the string theory landscape, not a single unique solution corresponding to our universe, but an astronomically large number of possible solutions, each describing a different possible physics. Our universe in this picture is one point in this landscape. The specific solution corresponding to our universe has not been identified. We do not know which of the 10 to the power of 500 solutions we are in. The landscape was initially seen as a crisis for string theory. If the theory has 10 to the power of 500 solutions, how does it predict anything? You can find a solution consistent with any set of physical constants, so the theory is unfalsifiable by any measurement of physical constants. Critics argued that string theory had abandoned the project of explaining why the constants have the values they do, and had instead produced a framework flexible enough to accommodate anything. But proponents of string theory pointed out that the landscape, interpreted in the context of eternal inflation, actually solves the fine-tuning problem. If eternal inflation produces different pocket universes with different physical constants, and if string theory provides the landscape of possible constants that can be realized, then the combination of eternal inflation and the string landscape gives a mechanism for populating the entire landscape with actual universes. Our universe is one solution in the landscape, actualized in one bubble of the eternal inflation, with the constants we have because those constants are compatible with our existence. This is the argument that connects string theory to the level 2 multiverse, and it has made the landscape and the multiverse central topics in high-energy physics discussions for the past 2 decades. Steven Weinberg's prediction of the cosmological constant from anthropic reasoning predates the landscape, but the landscape provides the physical mechanism that makes the anthropic argument more concrete. If the cosmological constant really does vary across different string theory solutions realized in different bubble universes, and if our existence selects for small values, then we have a physical explanation for the fine-tuning. Whether this is satisfying depends, again, on your philosophical priors about what scientific explanation requires. Many physicists find it deeply unsatisfying. David Gross, one of the founders of quantum chromodynamics, has been particularly vocal in his opposition to the landscape and the anthropic principle, arguing that they represent a retreat from the goal of explaining the constants and a betrayal of the scientific spirit. Others, like Leonard Susskind, have argued that the landscape is what the theory gives us, and that refusing to accept its implications because they are philosophically uncomfortable is itself a betrayal of scientific honesty. If the physics points to the landscape, you cannot just decide it must be wrong because you do not like what it says. The debate continues. And it is one of the most interesting debates in fundamental physics today, precisely because it is not just about physics, but about what physics is for, what it means to explain something, and what counts as scientific progress. I want to spend some time on the relationship between the multiverse and consciousness, because it is something that gets discussed a great deal in popular presentations of these ideas, and often in ways that are not quite right. The anthropic principle, in its most basic form, says that we should not be surprised to find ourselves in conditions that allow for our existence. This is almost trivially true and follows from nothing more than the fact that if the conditions did not allow for our existence, we would not be here to be surprised. It is a selection effect. But there is a version of the anthropic principle that goes further, that incorporates not just our existence as physical beings, but our existence as conscious observers. Some discussions of quantum mechanics and the measurement problem suggest that consciousness plays a special role in determining which outcomes occur, that the wave function collapses when a conscious observer makes a measurement. This is not the mainstream view in physics, and it is not what the many worlds interpretation says. Many worlds specifically removes the special role of consciousness by saying that the wave function never collapses and that consciousness is not fundamentally different from any other physical process. But the idea that consciousness might play a special role in physics keeps coming back, in various forms, because the measurement problem in quantum mechanics is genuinely hard, and some of the proposed solutions do invoke observer-dependent facts. The many minds interpretation, a variant of many worlds, puts consciousness at the center of the branching. Some interpretations of quantum mechanics posit that the wave function does collapse, and that the collapse is triggered by something like irreversible physical processes, which may or may not be connected to consciousness, depending on how you define it. I am not going to try to resolve the debate about consciousness and quantum mechanics tonight, because it would take another very long video, and because the issues are genuinely difficult and not close to resolution. What I will say is that the popular view that the universe needs consciousness to exist, or that consciousness creates reality by observing it, goes well beyond anything that mainstream physics actually says. The many worlds interpretation, which is the most serious theoretical response to the measurement problem, explicitly removes any special role for consciousness. It says that the universe branches into all possible outcomes regardless of whether any conscious being is present to observe them. The anthropic principle, in its scientifically respectable form, does not say that consciousness creates the universe. It says that we observe conditions compatible with our existence because we could not observe conditions incompatible with our existence. The selection is made by our existence, not by our consciousness. The two are very different. Now let me talk about what the multiverse implies for the idea of scientific laws. This is a deep question that is rarely discussed in popular presentations. In a single universe with fixed physical constants, the laws of physics are, in some sense, absolute. They apply everywhere and at all times. They are, as far as we can tell, the same in the Andromeda galaxy as in the Milky Way. They were the same in the early universe as they are now. They are, in this sense, truly universal laws, but in a multiverse where different regions have different physical constants, the laws of physics as we know them are not universal. They are local. They are the laws of our patch of the multiverse, our bubble universe. Other bubbles have different laws. The electron has a different mass. The speed of light might be the same, being a fundamental constant of spacetime, but the masses and charges of particles might differ. The nuclear force might be stronger or weaker. In this picture, what we call the laws of physics are really the local bylaws of our neighborhood. They describe how things work here in our bubble, but they are not the ultimate laws that govern all of existence. There might be deeper laws, laws that govern the entire multiverse and that determine the distribution of constants across bubbles. In string theory, the deeper laws would be the equations of string theory, and the constants of each bubble would be determined by how the extra dimensions are compactified in that bubble. This is a radical reconceptualization of what physical laws are. Instead of being absolute and universal, they become conditional and local. Instead of being the final answer to how things work, they become the effective description of how things work in one region of a much larger structure. Whether this is true, whether the laws of physics are local or universal, is connected to whether the level 2 multiverse is real. And whether the level 2 multiverse is real is connected to whether eternal inflation is correct and whether string theory provides the landscape of possible constants. These are all open questions, but the philosophical implication is worth sitting with. If the laws of physics that we have spent centuries discovering and refining and testing are not universal but local, then our project of understanding the universe changes character. We are not discovering the ultimate rules of existence. We are mapping the local environment, learning the rules of the game as played in this particular bubble. The deeper rules, the rules of the whole multiverse, might be different in kind from what we are used to, mathematical structures of a kind we have not yet encountered. This is humbling. And it is also, in a strange way, exciting, because it means there is potentially much more to discover, not just within our universe, learning more about the particles and forces and the evolution of the cosmos, but about the structure of the multiverse itself, about the deeper principles that generate the landscape of possible universes, about what the mathematical structure of everything looks like from a perspective that encompasses more than our bubble. We are nowhere near that perspective. We can barely see the edge of our own observable universe, but the question of what lies beyond and of what the ultimate structure of everything is a question that science is now, for the first time in history, beginning to engage with seriously. Not as speculation, not as philosophy dressed up in mathematics, but as genuine scientific inquiry, with specific predictions and specific searches and specific progress. The multiverse is at the frontier of that inquiry, and the frontier is where the most interesting work in science always happens. Sleep well knowing that you live in a universe that may be one of an incomprehensible number, that the physical constants that make your existence possible may be local bylaws rather than universal truths, that the mathematics of your universe may be one instance of a vastly larger mathematical landscape, and that right now, somewhere, physicists and philosophers are working to figure out what any of this means. That is the world we live in. Strange, uncertain, and more interesting than we thought. Good night. Let me go somewhere that rarely comes up in discussions of the multiverse, but that I find genuinely important. It is the question of what the multiverse means for the concept of uniqueness, for the idea that any particular thing, any event, any person, any moment is unique and unrepeatable. In ordinary experience, uniqueness seems obvious. You are the only you. This particular moment has never happened before and will never happen again. Every configuration of the universe is, in principle, different from every other configuration. Even the most mundane event, a particular leaf falling from a particular tree on a particular afternoon, has a specific physical configuration that has never been precisely replicated in the history of the universe and will never be precisely replicated again. This sense of uniqueness is deeply connected to meaning. We value things partly because they are unrepeatable. A sunset is beautiful partly because it will not come again exactly like this. A moment with someone you love has weight partly because this specific moment, this specific configuration of experience will not recur. The irreversibility of time, the one-directionality of events, is connected to the sense that things matter, that choices matter, that this particular life is something singular and valuable. But in a spatially infinite level 1 multiverse, this sense of uniqueness is complicated. Your nearest copy exists at an incomprehensible distance, but the copy exists. This moment, this configuration of you reading this has been replicated, is being replicated right now, in another region of the same space. Not in a parallel dimension, not in another time, but in the same spatial universe, unimaginably far away but physically continuous with here. Does this diminish the meaning of this moment? Does it make you less unique? I do not think it does, and here is why. The distance to the nearest copy of this moment is so large that it might as well be infinite for any practical purpose. No signal, no influence, no causal connection of any kind will ever reach from here to there or from there to here. The copy is causally isolated from you forever. Its existence has no effect on your life, no effect on your choices, no effect on what this moment means to you or to anyone who knows you. The uniqueness that matters for human experience is not metaphysical uniqueness, the guarantee that there is literally no other configuration in the entire universe that resembles this one. The uniqueness that matters is causal uniqueness, the fact that this moment is embedded in a specific causal history, connected to specific people and events, with consequences that flow forward from it in ways that are real and particular and yours. The copy exists, but it is not you. It has its own causal history, its own future, its own connections. You are not the copy. You are this here now. The many worlds interpretation raises this question more acutely. If every quantum event branches the wave function, then there are branches in which versions of you made different choices. Are those branches real? Are those versions of you real? And if they are, does your choice here matter, given that another version of you made the other choice in another branch? This is a version of the fatalism worry about determinism, updated for the multiverse, but the response is similar. Even in a world where the other branch exists, the branch you are in is the one that matters for your experience, for your connections, for the consequences of your actions. The other branches are not accessible to you. You cannot know about them, cannot communicate with them, cannot be affected by them. Your choices determine the branch you are in, and that branch is the one you will continue to inhabit. Moreover, the many worlds branching does not make your choices irrelevant. It makes them more important in a certain sense. Every choice you make determines which branch you enter and continue in. The other branches are not alternatives you are giving up. They are separate, inaccessible trajectories that have nothing to do with your ongoing experience. Your choice here is the one that matters for you. I raise these issues not because they are resolved, but because they are part of what it means to take the multiverse seriously. If the multiverse is real in any of its forms, it has implications for how we think about identity, uniqueness, meaning, and choice. Those implications are worth thinking about honestly, even if they are uncomfortable, even if they do not lead to clean, reassuring conclusions. The universe, if the multiverse is real, is a place where everything that can happen does happen, somewhere, somehow, in some branch or region or bubble. It is a place where the specific configuration of events and choices that constitutes your life is one of an astronomical number of variations on a theme. And it is also, simultaneously, a place where this moment, this specific configuration, is the one you are living, the one that has causal consequences for your future, the one that is embedded in the network of relationships and histories that define your world. Both of these things can be true. The vastness of the multiverse and the significance of the specific are not in conflict. They are different ways of describing the same reality at different scales. Let me return to the physics one more time, because there is a development I have not mentioned yet that is important for understanding the current state of multiverse science. It is the AD-SCFT correspondence, sometimes called holography, and it has transformed our understanding of the relationship between gravity and quantum mechanics in ways that bear on the multiverse question. The AD-SCFT correspondence, proposed by Juan Maldacena in 1997, is a precise mathematical duality between two apparently different theories. On one side is a theory of gravity, specifically string theory in an anti-de Sitter spacetime, a particular curved geometry. On the other side is a quantum field theory, specifically a conformal field theory, living on the boundary of that spacetime. The two theories are exactly equivalent. Any calculation you can do in one can be translated into a calculation in the other. They describe the same physics in two apparently different languages. This is called holography because it suggests that the physics of a three-dimensional spacetime with gravity is completely encoded in a two-dimensional theory on its boundary. The three-dimensional bulk physics is holographic, projected from the two-dimensional boundary. The analogy to a hologram, where a three-dimensional image is encoded in a two-dimensional surface, gives the idea its name. AD-SCFT has been spectacularly successful as a mathematical tool. It has provided new ways to calculate properties of strongly coupled quantum systems that are otherwise intractable. It has given insights into quark-gluon plasma, into condensed matter systems, into the nature of black hole thermodynamics. It has become one of the most important ideas in theoretical physics of the past 30 years. And it has deep implications for the information paradox in black hole physics, which I discussed in the context of the black holes video. If AD-SCFT is correct, and there is every mathematical reason to think it is, then the physics inside a black hole is completely encoded in the physics on the boundary of the spacetime. Information about what falls into the black hole is preserved in the boundary theory, even if it seems to be lost in the bulk description. AD-SCFT suggests that information is not destroyed when things fall into black holes, resolving the information paradox in the AD-S setting, though the implications for realistic black holes in our universe are still being worked out. The reason this matters for the multiverse discussion is subtle but important. AD-SCFT provides a concrete example of a case where two apparently different descriptions of reality, gravity in the bulk and a quantum field theory on the boundary, turn out to be exactly equivalent. Neither description is more fundamental. They are dual descriptions of the same underlying physics. This kind of duality, where apparently different theories describe the same reality, is a recurring theme in string theory and in modern theoretical physics. The string landscape contains many apparent solutions that turn out to be related by dualities, equivalent descriptions of the same physics in different mathematical language. This means the number of truly distinct solutions in the landscape may be smaller than the raw count suggests, though it is still very large. More importantly, the existence of dualities suggests that our concepts of what is fundamental, of what the basic description of reality is, may be more flexible than we thought. There may not be a single fundamental description. Different descriptions may be equivalent, each appropriate for different ranges of parameters or different questions. This is a very different picture from the classical vision of physics, in which there is one true description of reality written in the language of some ultimate unified theory. The relationship between AD-SCFT and the multiverse is still being worked out, but the general direction it points is toward a view of reality as described by multiple equivalent frameworks, none of which can claim to be the uniquely fundamental one. This is philosophically rich and scientifically important, and it is one of the ways that the most technical developments in theoretical physics connect to the deepest questions about the nature of existence. I have spent a long time with you tonight, going through the different types of multiverse, the evidence for and against each, the philosophical debates they generate, the specific physics of eternal inflation and many worlds, and the string landscape and holography. It is a lot to hold. But I think it is worth holding, because these are genuine questions about the nature of reality that humanity is now equipped, for the first time, to engage with seriously. We are not speculating blindly. We have theoretical frameworks of extraordinary power and mathematical precision. We have observations that constrain the possibilities. We have specific predictions that are being tested. The answers are not in yet. The multiverse remains one of the most contested ideas in physics and philosophy. But the question itself, the question of whether our universe is all there is or one of many, is one of the deepest questions that can be asked. And engaging with it seriously, following the physics wherever it leads, is what science at its best looks like. The universe is larger than we thought. It may be unimaginably larger. The physical laws we have spent centuries uncovering may be local rather than universal, specific to our bubble rather than governing all of existence. The reality we inhabit may be one point in a mathematical landscape of incomprehensible richness. Or it may not. We are working to find out. That work is ongoing. The search for bubble collision signatures in the cosmic microwave background continues. The development of string theory and its landscape continues. The philosophical analysis of the many worlds interpretation and the nature of quantum probability continues. The James Webb Space Telescope and its successors are mapping the high redshift universe and the conditions under which inflation ended, constraining models and opening new questions. We are at the frontier. And the frontier, as always in science, is the most interesting place to be. Sleep well tonight knowing that the physics of the multiverse is not idle speculation but active science, pursued by the most rigorous and creative minds in the field, using the most powerful tools ever built, aimed at one of the deepest questions ever asked. What is there? We are finding out. Good night. There is one more thing I want to explore before we close. It is something that sits at the intersection of the physics and the philosophy, and it is, I think, the most important question that the multiverse raises. It is the question of what the multiverse means for the project of science itself. Science works by making predictions and testing them. You have a theory. The theory makes specific, quantitative predictions about what you will observe in experiments. You perform the experiments. If the predictions match the observations, the theory is supported. If they do not, the theory is refuted or needs modification. This is the hypothetico-deductive method, the core of the scientific enterprise, and it has been extraordinarily successful over the past 4 centuries. The multiverse complicates this picture in a specific way. If the multiverse contains all possible observations, or even a very large fraction of all possible observations, then the question of what the theory predicts becomes ambiguous. A theory that is consistent with every possible observation is not a scientific theory in the traditional sense, because it cannot be falsified. There is no observation that would count against it. This is the core of the testability objection to the multiverse. If eternal inflation generates pocket universes with all possible values of the physical constants, and if we are in whichever pocket universe is consistent with our existence, then the theory is consistent with any set of constants we might observe. It makes no sharp prediction. It cannot be falsified, and therefore the objection goes, it is not science. This objection deserves a serious response. And the response comes in several parts. First, the multiverse does make predictions at the level of statistics. It predicts that among all observers in the multiverse, certain values of the constants will be more common than others. If you know the distribution of constants across the multiverse, you can calculate the probability that an observer like us would observe constants in a certain range. The prediction of the cosmological constant by Weinberg is of this type. It is a statistical prediction, not a sharp prediction about a specific value, but it is a prediction nonetheless, and it has been confirmed. Second, specific models of the multiverse make additional predictions that are not just about the constants. The eternal inflation plus string landscape model makes predictions about the shape of the primordial power spectrum, about the absence of certain types of signals, about the statistics of bubble collisions. These predictions can be tested, and some of them have been tested, with results that constrain the model. Third, and most importantly, the testability standard itself is not as clear-cut as it might seem. Many accepted scientific theories make predictions that are extremely difficult to test in practice, or that involve unobservable components. String theory was accepted as a serious scientific framework for decades before any predictions were claimed for it, purely on the basis of its mathematical consistency and its potential for unification. Dark matter has never been directly detected, but it is accepted as real based on its gravitational effects. The interior of black holes will never be observed. The Big Bang itself, the moment of zero time, is beyond observational reach. Science routinely accepts the existence of things we cannot directly observe, when those things are implied by our best theories, and when their existence explains what we do observe. The question for the multiverse is whether it meets this standard, whether the multiverse is implied by our best theories, inflation and quantum mechanics, and whether the existence of the multiverse explains features of our universe, specifically the fine-tuning of the constants that would otherwise require explanation? The answer is arguably yes to both. Eternal inflation is a generic consequence of many models of inflation that are independently well-motivated. The multiverse of bubble universes is what you get when you take inflation seriously and follow it to its logical conclusion. And the fine-tuning problem, the extraordinarily precise values of the constants, is explained, at least in outline, by the anthropic argument in the context of the multiverse. Whether this is enough to qualify the multiverse as science rather than metaphysics is a question that will not be resolved quickly. The debate is ongoing among physicists and philosophers of science. But it is worth noting that the multiverse is not being proposed frivolously or for philosophical satisfaction. It is being proposed because the physics points to it, because taking seriously the theories we have the best evidence for leads us in this direction, and because it provides the most natural current explanation for some of the deepest puzzles about why our universe is the way it is. That is not nothing. That is, in fact, quite a lot, and the ongoing refinement of predictions, the ongoing search for bubble collision signatures, the ongoing development of the theoretical framework, the ongoing philosophical analysis of what the multiverse means for scientific methodology, all of this is making the question more precise and the answers more grounded. Progress is being made, even if the final answer is not yet in sight. I want to end with something about the psychology of engaging with these ideas. Because I think there is a temptation, when confronted with the multiverse and all its strange implications, to retreat, to say that it is too speculative, too philosophical, too far from ordinary experience to be worth taking seriously. To prefer the comfortable picture of a single universe, our universe, finite and comprehensible, and the totality of existence. That temptation is understandable, but I think it should be resisted. The history of science is a history of expanding the domain of what we take seriously. The heliocentric model was resisted because it displaced the Earth from the center and made us seem less special. The discovery of other galaxies was resisted because it displaced the Milky Way from a central position and made the universe seem indifferently large. The Darwinian theory of evolution was resisted because it connected humans to other animals and made our emergence seem contingent rather than designed. In each case, the resistance was understandable. In each case, the science was right and the resistance was wrong. And in each case, what seemed like a diminishment of human significance turned out to be an expansion of understanding that made the universe more interesting and more rich than the previous, more comfortable picture had allowed. The multiverse is the current frontier of this expansion. It suggests that our universe, vast as it is, may be one of many, that our physical laws, elegant as they are, may be local rather than universal. That our existence, improbable as it seems, may be one instance of a much larger phenomenon. That the question of why anything exists at all may be addressable in a new way by physics. This is not diminishment, it is enrichment. It is the universe showing us, once again, that it is larger and stranger and more interesting than we thought, that the limits of our observation are not the limits of what exists, that the questions we can ask are deeper than the answers we currently have. Engaging with the multiverse, seriously and honestly, is part of what it means to be a curious species living at a remarkable moment in the history of scientific understanding. We have the tools to ask these questions seriously. We have the theories to make progress on them. We have the instruments to search for evidence. And we have, most importantly, the willingness to follow the physics wherever it leads, even when it leads somewhere uncomfortable. That willingness is the most important thing. It is what has driven every major advance in our understanding of the universe, and it is what will drive the next ones. The multiverse is out there, or it is not. We are working to find out. Sleep well. The universe or universes will still be here when you wake up, and so will the questions. And questions, it turns out, are the most interesting things there are. Good night. Let me bring you to one final idea that I think deserves its own space in this conversation. It is the concept of the measure problem in eternal inflation, and it is one of the most technically difficult and philosophically interesting challenges in the whole multiverse framework. The measure problem goes like this. Eternal inflation produces infinitely many pocket universes. In an infinite multiverse, every type of universe that can exist does exist, infinitely many times. The question of what we should expect to observe, of what is typical or probable in this multiverse, requires calculating the fraction of observers who see any given set of physical constants. But when you have infinitely many of everything, calculating fractions requires a measure, a way of comparing infinite quantities. The choice of measure, of how you count and compare observers in different parts of the multiverse, turns out to matter enormously for the predictions. Different measures give different predictions for what we should observe. Some measures predict that we should be in the smallest possible pocket universe, because smaller universes are more numerous in some counting procedures. Others predict that we should be surrounded by a cosmological constant that is exactly at the upper bound compatible with galaxy formation. Still others give different predictions. The measure problem is not solved. It is one of the central unsolved problems in eternal inflation and in the multiverse more broadly. Without a well-motivated measure, the multiverse framework cannot make precise statistical predictions. It can make qualitative arguments, like the ones that led Weinberg to predict a small cosmological constant, but it cannot make the kind of precise quantitative predictions that are the gold standard of physics. This is a serious limitation, not a fatal one necessarily, because the measure problem might eventually be solved, either by finding a physically motivated measure or by finding that different reasonable measures all give similar predictions for the quantities we care about. But it is a genuine gap in the framework, and honest engagement with the multiverse requires acknowledging it. The measure problem illustrates something important about the current state of multiverse physics. The framework is advanced enough to generate specific questions and to identify specific obstacles to answering them. That is progress compared to the early days when the multiverse was purely speculative. But it is not yet at the point where the obstacles are resolved and the predictions are secure. That is the honest status of the field. Important progress has been made. Important problems remain. The work continues. There is something I find deeply satisfying about the structure of this situation. The multiverse is one of those ideas that reveals as you dig into it that it is harder and richer than it first appeared. On the surface, it seems like a simple idea. Many universes, different constants, anthropic selection. But as you go deeper, you find that each step raises new questions. What is the measure? What generates the landscape? Is the string landscape really as large as claimed? What does it mean for a quantum branch to be real? How do you derive the Born rule? What is the relationship between different levels of the multiverse? Each of these questions is a research program in itself. Each of them is being actively worked on by serious physicists. and each of them, when answered, will generate new questions of its own. The frontier does not shrink, it expands. That is what a rich and important scientific question looks like, not a question with a quick, clean answer that closes the book, but a question that opens doors, that reveals new territory, that draws you deeper into the structure of reality the more seriously you take it. The multiverse is that kind of question, and I am glad that physics has reached the point where it can ask it seriously. We are a species that evolved to survive on the African savanna. Our brains are tuned for tracking predators and finding food and maintaining social relationships. The ability to reason about the structure of spacetime, about quantum mechanical branching, about the statistics of observers in eternal inflation, is not something evolution designed us for. It is something we built painstakingly over millennia through the accumulated work of countless individuals who were curious and careful and honest about what they knew and what they did not. The multiverse is the current edge of that accumulated work. It is where the tools we have built, the mathematics, the physics, the philosophy of science, are being pushed to their limits. And at those limits, we find ourselves asking questions about what exists beyond the observable universe, about whether the laws of physics are universal or local, about the ultimate nature of physical reality. That we can ask these questions at all is remarkable. That we have made as much progress on them as we have is extraordinary, and that there is still so far to go, that the answers are not yet in and the frontier is still wide open, means that the most interesting work in this area is still ahead of us. We are at the beginning of understanding the multiverse in whatever form it might take, and beginnings in science are the most exciting times to be at a question. Sleep well. The universe is out there, vast and old and full of questions that we are only beginning to ask properly. The multiverse may or may not be real, but the physics that points toward it is real. The questions it raises are real, and the work of answering them is the most important intellectual project of our time. Good night. Let me take you through one more concrete piece of physics that connects the multiverse to something we can actually observe. It is the spectral index of primordial fluctuations, and it is one of the places where inflation, and by extension the multiverse, makes a specific, testable, and confirmed prediction. When inflation ended in our bubble universe, the inflatoned field released its energy and the universe reheated. But before that, during inflation, the quantum fluctuations of the inflatoned field were stretched to cosmic scales. These fluctuations became the seeds of the large-scale structure we see today, the distribution of galaxies, the temperature fluctuations in the cosmic microwave background. The statistical properties of these primordial fluctuations are described by a power spectrum, a mathematical function that tells you how strong the fluctuations are at different length scales. Simple models of inflation predict that this power spectrum should be nearly scale invariant, meaning the fluctuations have roughly the same amplitude at all length scales, with a small tilt. The degree of tilt is characterized by a number called the spectral index, denoted ns. A perfectly scale-invariant spectrum has ns equal to 1. Simple models of slow-roll inflation predict ns slightly less than 1, by an amount that depends on the specific model of inflation, but is typically around 0, 96 to 0, 97. The Planck satellite measured the spectral index from the cosmic microwave background and found ns equal to 0.965 plus or minus about 0.5. This is a precise measurement, and it is precisely consistent with the predictions of simple slow-roll inflation. the measured spectral index is about 3.5 sigma away from 1, confirming the slight tilt predicted by inflation. This is a genuine predictive success for inflation. The spectral index was predicted to be slightly less than 1, and it is. The specific value is consistent with simple models. This confirmation is one of the main reasons physicists take inflation seriously, and by extension, one of the reasons to take seriously the multiverse that inflation implies. But the spectral index is just one of several predictions of inflation. The amplitude of the fluctuations, the angular size of the variations in the cosmic microwave background, the statistical character of the fluctuations, all of these are predicted by inflation, and all have been confirmed to varying degrees. The detailed pattern of peaks and troughs in the power spectrum of the cosmic microwave background is one of the most precisely measured things in all of cosmology, and it fits the inflationary predictions with remarkable precision. These confirmations do not prove that eternal inflation is correct. Simple inflation, without the eternal component, could explain all of these observations. But eternal inflation is a generic feature of many inflationary models, and there is no known mechanism that would make inflation non-eternal in a natural way. Once you have inflation, you almost inevitably have eternal inflation, and once you have eternal inflation, you almost inevitably have a level 2 multiverse. The path from the observed spectral index to the multiverse is long and involves many steps, each of which can be questioned. But the observational confirmation of inflation is real, and it is one of the strongest pieces of evidence we have for the physical framework that most naturally implies a multiverse. Understanding this is important for evaluating the multiverse claim honestly. The multiverse is not being proposed in isolation from observation. It is being proposed as a consequence of a framework, inflation, that is empirically supported. The question is not whether to believe in the multiverse on purely theoretical grounds. The question is whether, given that inflation is almost certainly correct in broad outline, the multiverse that follows from it should be accepted as physically real. That question connects back to all the philosophical issues we have been discussing. What counts as real? What counts as an explanation? What counts as science? These are hard questions, and the multiverse sits at their intersection. But they are questions worth asking. And we are right now better equipped to make progress on them than at any previous point in history. We have the observations, we have the theory, we have the philosophical framework. What we need is patience, intellectual honesty, and the willingness to follow the evidence wherever it leads. That is what science is. And the multiverse is where science is going right now. Whether the universe you inhabit is the only one, or one of an incomprehensible number, you are part of a species that is asking that question seriously. That built the instruments to search for the answer. That developed the mathematics to frame the question precisely. That has the philosophical sophistication to recognize the depth of the challenge. That is worth something. That is worth a great deal. Sleep well. The questions are bigger than we are. But we are asking them anyway, and sometimes that is enough. Good night.